My name is Patrick Bellew. I'm the principal of Atelier 10. We're environmental designers, environmental consulting engineers, specialising in design of green buildings.
My name is Emma Marchant. I'm a senior environmental designer at Atelier 10. My background is that I'm a qualified architect. I know that you're interested in biomimicry. Are there any lessons that you could give to architects to inform their building forms from nature?
Yeah, there certainly are. In the early days of my training, I was taught about two particular areas of sort of working with nature. One was the Eskimo and his igloo as the sort of the perfect sustainable structure, where the basic understanding of conduction, convection, radiative heat transfer, and airflow, using simply ice blocks and skins, converts the structure from converts the weather outside, if you like, from -20, -30 degrees centigrade in a howling gale to being survivable at or around freezing overnight. And that's done because the Eskimo understands by instinct somehow how to do these things. Extending that into animal architecture, I was introduced by my professor at university, who was a gentleman called Derek Kroon, to the wonders of the termite. And there are two particular types of termite that we always looked at. One was called a compass or magnetic termite. So called because all of the nests are built orientation exactly north-south, and the idea is that they need to get the nests to be high in order to catch breeze about 4 meters off the ground in the plains of Australia, and then they need so that height gets an updraft of air. But if they built the nests very wide, they would catch too much sunlight and they'd overheat. So they build these long chisel-shaped nests that basically get a minimum amount of sunlight in the sunlight exposure at noon, but plenty of sunlight exposure after a cold night, first thing in the morning, and in the evening before the cold night, on the long sort of flat face of the nest. So that you see rows upon rows of these nests in Australia, out in the plains. Now, these creatures are building entirely by intuition. They don't know. They have no architecture degree. They're blind. Yeah. They're building intuitively. And so there's a kind of intuitive understanding of how heat flows and energy flows. If you go to Africa, there's the Barossa termite, which David Attenborough went into the nest of as part of the series Life on Earth. And this vast underground chamber, which is the climate control mechanism for the nest, the termites are able to control the flow of air through the nest by blocking and unblocking holes in the structure. And their sole purpose is to keep the queen, who lives at the centre, who's this sort of creature about sort of this big, at exactly 30 to 31 degrees centigrade, right through the year. Fussy creature. Yeah. But she produces 25,000 eggs or so a day, so she probably is right to be crabby. So she likes to be kept at this controlled temperature. And by some mechanism we don't really understand, some chemical communication mechanism, they communicate temperature, too hot, too cold, to certain of the ants who have a job of blocking or unblocking holes in the structure in response to these temperatures, which allows the air to be drawn in through some pipes in the ground, tubes in the ground, into an underground chamber. And the tubes they unblock are in the high part of the nest. The air rises up through by passive stack effects and cools the structure down. If that's not enough, they add moisture from the nest to provide evaporation, and if that's not enough on a very hot day, they will go down to the water table, maybe 20 or 30 metres below ground level, carrying a leaf stem or a seed pod, bringing up water from deep underground, putting it into this underground chamber to provide evaporation and produce a cooling effect. So a combination of thermal mass, evaporation, and storage, allowing this sort of extraordinary architecture to be controlled to a very, very high degree. And to me, that's part of the knack that architecture lost. It's this intuition. Now, I've worked with structural engineers all my life, and I worked first for Bureau Happold, Ted Happold was a structural engineer, and then with Atelier 1, Neil Thomas was a structural engineer. And I've always been very inspired by Buckminster Fuller, another famous structural engineer. And what they were good at was doing more with less, making the materials, making the buildings work in the simplest possible way.
I think many architects maybe aspire to that as well, or feel that they have intuition, or understand things intuitively, such as basic orientation. And kind of where the sun is. But through my experience of working at Atelier 10, I've sometimes been surprised to find that architects, maybe they understand the basic principles, but they're not applying them properly. So how do you think we can take these basic principles and theories and actually start to apply them to buildings?
Well, we've been working with thermal mass in buildings for really all the time that I've been in practice. It's always seemed to me to be this most sensible way of trying to moderate between varying occupancies in buildings, the daytime condition, the nighttime condition, particularly in our climate in the UK, where we generally have cool nights followed by warm days, although that's changing a little bit. So I've always worked with thermal mass. When we started doing some larger projects, and in particular the first one was the Earth Centre in Doncaster, we were faced with the problem of trying to condition a very large 6,500 metre squared, 8 to 10 metre high gallery space, which was going to be at the centrepiece of the exhibition. And thermal mass didn't really come into it. Once you're 10 metres away from a piece of thermal mass, it's not going to help you in terms of environmental control very much. Although we did have a big massive roof and grass roof on top of it. And here the structure engineer was struggling to build, he wasn't struggling, but the structure engineer was needing to build a very large raft foundation because the building was founded on an old colliery spoil heap, and so the ground was very bad. It straddled two fault lines, and so the building had to be on a raft. So the structure engineer was looking at a very thick raft. So I just had a sort of eureka moment, I think I was in the bath probably, and thought, well, maybe we should hollow out this slab and turn it into some sort of underground series of passageways. And I think this is how it happened. And so I produced a sketch, a series of sketches that I sent to the architect and said, why don't we hollow it out and make a sort of labyrinth under the floor and use that as our airflow. And it's very much like an anthill works. It's the air coming in from outside, passes across lots of surfaces before it's introduced into a living space, just as it does in an anthill. Although we would control, instead of having people blocking and unblocking holes with mud, we would have some small, low-powered fans that would do that job. So it was really taking the principles of this sort of bioclimatic architecture and trying to apply it to a building. And we went ahead and built that building very rapidly. It's a series of concrete and blockwork cells below the ground, below the feet, and then the air comes into the space through displacement air, which is air from the bottom of the space, which again is something that we've pioneered and championed right the way through the life of Atelier 10, as you well know. It's part of our sort of toolkit, basic toolkit. And we found that the combination of the underground storage and the displacement air supply was sufficient to require no air conditioning at all through the summer months. And because the climate of North Yorkshire could provide adequate conditions really all of the time.
I have to say, why do you think more architects aren't, or more projects aren't incorporating these kind of technologies or approaches? Well,
I think just as in an anthill, the volume of space, the amount of space that's taken up by the environmental control system is probably half the volume of the building.
Right.
And with the cost of buildings, clearly one is limited to how much you can take over all the space with equipment. The labyrinth at the Earth Centre was effectively the whole area of the building at sort of a 1.6 metre high, so it was like building a basement. So it was quite an expensive element. So I guess that cost is the principal thing. But they would have had to build this deep foundation anyway, and actually what we did was take out some of the concrete, not put any in, but we did make it slightly more complicated to build. So our successful structures like that have tended to be on found space that was being built anyway. If you have to dig the ground down an extra metre to put this thing in, it starts to become prohibitively expensive for the benefits that you make.
I'm aware you've applied this though at a much bigger scale in Australia on Federation Square. And that was, that's actually become quite an iconic structure as well, which is another exciting aspect of it, that it's no longer just sort of a hidden environmental system. It's become something that people actually pay to have a tour around and to see and to view. Can you tell us more about how that one worked?
Yeah, that came about in a very strange way. We won the competition with lab architecture to build the enormous complex at Federation Square in Melbourne, and we were trying to find somewhere to put a labyrinth. And this the whole project is built above the rail tracks going into Melbourne railway station on a crash deck. And then above that is a sloping piazza which forms the not-so-square square, which has 20,000 people can stand on and look down at the big screens and look at events and so on going on. And there was this void in between that had nothing happening inside. So we sort of thought, well, we could put a labyrinth in there. And it became very much, the structural engineer really picked up on the design of it. This is the great thing about collaborative ventures, that he took it to a level I didn't really expect him to, that he made these amazing rippled walls that became very iconic. Mm-hmm. Simply, they were fabricated on site out of concrete, so it was very simple, but they look great. And they're up to 4 metres high. Mm-hmm. And so we built this enormous underground structure, which does a very similar job to the one at the Earth Centre, but on a bigger scale. Now, the weather in Melbourne goes up to... The weather? Perhaps the temperature in Melbourne goes up normally to a maximum of about 38 degrees centigrade, although last couple of weeks it's been up in the high 40s, of course, with the fires there. But the design condition was about 38, 39, which is considerably warmer than the UK. They also have quite warm evenings, but mostly they have cool nights as the weather comes in from the South Pole, effectively, from the Southern Ocean. And when we analysed the weather, we found that we could actually eliminate air conditioning completely in this vast atrium space that runs the entire length of the scheme, simply by using this thermal mass. And we went and presented to them on two principal points about the cost of the system and the payback period. Mm-hmm. But the nice political part of the story is that when I presented it, I was asked the question as to whether Sydney had a labyrinth. Mm-hmm. Because Sydney were very much the green city at the time with the Olympics going on. I said, no, Sydney hasn't got one. They said, in that case, we'll have one. Mm. And so the labyrinth became part of the scheme. That's a slightly jokey story, but that really did happen. Initially, there was no intention that anybody would go in there, but now they do run tours every Sunday, so you can go and see it, and it's in all the books about the building. And so I think, in a sense, making the environment manifest is quite an important part, because so often, in the work that we do is basically invisible architecture. Yeah, it's invisible architecture. It's what we're doing is informing how the air flows, how the sunlight moves through a building, how the daylight moves through a building, and people are generally only aware of the buildings that fail in that regard. Yeah. What we try and do is create buildings that succeed and that work, buildings that don't overheat too much, that are comfortable most of the time, or all of the time, preferably. So that's this whole notion of sort of invisible architecture. And what's nice about the labyrinths is they really do manifest sustainable design in the strongest possible way.
I think this is a great message for architects as well, because something that architects seem to focus on, or at least at the moment there seems to be anxiety about, is how do we find the next exciting technology that's going to provide us with renewable energy, that's going to give us the way forward. And I think, unfortunately, they seem to miss the opportunity every single time to actually maximise the energy they can save in their buildings through effective design, and that actually they hold the key to reducing carbon emissions, if you like, most significantly through the actual built form, the kind of the unsexy stuff, as it's so called, but actually it's the building, the part that they're most passionate about. Yeah,
I think 2 points to that. One is that as we move towards a zero carbon building system, any kind of system like this that dramatically reduces the carbon emissions of equipment. So here we just run 2 fans. We don't run any kind of cooling plant or heating plant. How much easier is it to get to zero carbon from there than it is from a normal building? And secondly, and almost more importantly, to me, sustainability is a lot about intergenerational thinking beyond our current iteration of the building. Yeah. So here's a civic building that's got a 100-year life, that had we put in conventional systems for cooling and heating that space, we would have had to change them every 20, 25 years. So in 25 years, you've got material and resource use. These concrete walls will still be there in 100 years' time, holding up the piazza, or 200 years' time. Yeah. And in those 200 years, you'll never have to change the equipment.
Which is some justification for using that much concrete, which on another hand could be considered to be less sustainable. But when you start to think about these things in the whole picture in terms of their embodied energy, and
absolutely,
then we can actually start to demonstrate the savings that way.
And I think it's important to differentiate between different building types. This is a civic building, which will be there for 200 years, hopefully, or 100 years, or whatever, who knows how long, compared to perhaps the more lightweight transient buildings, such as, dare I say, schools, office buildings, and those sorts of things that tend to maybe only last 25 or 50 years. But so it's very important to differentiate between them. But I think that's the great strength of this kind of work, is that it has longevity. Yeah. And it's not just about bolting a solar panel on a building and calling it green. Yeah.
Would it be fair to say that we've moved from real guesswork and basic principles to incredible precision?
Yeah, I'd say that's probably true. In the last 15 years that we've been doing this, it's really, really changed. We used to use basic laws and some very simple calculations and very simple principles and instinct to decide whether a system was going to work. It's like when you're training an architect to do structures. Mm-hmm. You would normally say, build a model. If the model breaks, the chances are... Out of spaghetti. If the model breaks, then the architecture, then your cantilever probably won't work.
Yeah.
It's much more difficult with environment, because environment is very dynamic. The temperatures are always moving around, the sunlight's changing day to day. And it used to be very difficult to do detailed calculations to show that a dynamic system would work. Now we have computer modelling that will model very, very complex buildings in a matter of minutes. It may take days to put the data in, but once you've got the data in, you can model scenarios, you can test things very quickly. And so with structures like the labyrinths and the earth pipes, which is something we're going to talk about in a second, another great televisual moment. Sorry. So with structures like the labyrinths, we were able to look at different alternatives, different amounts of thermal mass, and try and optimise them in a way that we couldn't possibly have done when we first started working on thermal storage systems a few years ago.
Yeah.
A very good example of that is how we've moved this from a professional client like a city council, where we built the Melbourne project, or a client like the Earth Centre, who's willing to take a gamble, because it's a building about sustainability, so it's a higher risk building, into a more commercial world, is the project we've done in Luton. It's called Butterfield Office Village, and this project is the first use in the UK of underground earth tubes on a large scale to provide cooling for a commercial office building. So the earth tube is like a labyrinth, but it's actually a concrete pipe that's buried in the earth. Mm-hmm. And instead of pouring lots of concrete into the ground to do your thermal mass, you actually use the mass of the earth as your heat store. Yeah. And basically how it works is that on a summer's night you draw air down the pipe into the building and cool the building down. And on a summer's day you also draw air through the pipe along into the building, where it comes up through the floor and comes out into the office spaces. And provides.
Termite idea.
It's another termite idea. I mean, that's exactly what termites do. They draw air down at tubes in the ground to provide free cooling, as we call it. So there's an office building which works with no air conditioning, but acts as if it was air conditioned as far as the occupants are concerned. Mm-hmm. Now that is starting to move us towards a much more sustainable, low energy, low carbon typology. It's not perfected yet. There are lots of complexities along the way about how people respond to it, how the market responds to it, what tenants want to do in their spaces, that makes it tricky, but it's doable.
Yeah. How did you go about convincing letting agents and the client to actually adopt this innovative system?
Yeah, the client was not so much of a problem. He was very interested in doing something different, and we showed him the numbers and we showed him the computer models.
So the
analysis was very important, and we predicted how many hours a year the building would be uncomfortable, and he said he thought he could sell that. He unusually then set up a series of meetings with letting agents, where I was asked to go to breakfast meetings and present the scheme. And I took a gamble, and I presented Termite Hills, and I presented the Villa Costozza in Italy, which is these cliff-top villas which are cooled by air that's blown through the cliff system underneath, and they come from the 18th century, 17th century, and are very effective sort of passively cooled structures. Mm-hmm. So I presented all those ideas to the agents, and they all munched their bacon rolls and thought, well, that seems like a possibility. And we got on and built them. And in terms of value, they've done very well, because the tenants who came to the business park in not a great market, they've all flocked to see this green and very highly publicised office village, which has actually let well in the market. Mm-hmm. And I think is now 80% let, which the client's very happy about.